All right, let's get into talking about building the Dirac Lagrangian from group theory. This is going to be maybe a longer video, but it's going to be super interesting. We're going to see a lot of interesting minute details that spinors play a big role in when we start developing this Lagrangian. And yeah, this is going to be super, super interesting. And again, if you like this kind of content, make sure to hit that like and subscribe button. Again, you can go into my Patreon page where you can get content early. And I'm sort of also in the process of making exclusive content as well that I will be posting on my Patreon page in the near future. Anyways, let's get into the topic. All right. We are building the free theory. Again, no interactions yet. We're building the free Lagrangian for the 1/2 0 0 1/2 representation. All right, so again, taken independently, these guys are left chiral spinors and right chiral spinors. And let's recall a few things, right? So recall this diagram we had sort of developed, right? We had these are the generators for, or in other words, the matrices that preserved the Minkowski metric, okay? And we said that so that those are these guys, and then these guys were used to build 1/2 0 representations and 0 1/2 representations. Again, these representations were representations of transformations that acted on spinors, not on vectors, right? So these guys were left chiral, and these guys were right chiral. Left chiral and right chiral. And then we said, well, how do these guys actually transform? These guys transform in these ways, right? So we could boost left chiral spinors, and we can boost right chiral spinors, or we can rotate them. And so from there, so that's the diagram we had developed up until now. Let's recall also that we were able to build charge conjugated spinors. So we did this before, just reminding ourselves what these are. The left chiral spinors again were subscripted, and right chiral spinors were superscripted, and then the left chiral charge conjugated, or the left chiral conjugated spinor was A with a dot on it down here downstairs, and then the right chiral conjugated spinor was A with no dot. Okay, so we had one or two videos going over these guys here, and this is a video that's going to put them into context. Right? It's gonna make them relevant. We need to, so this is exactly why we needed to do that. We need charge conjugated spinors to construct invariant objects in this representation under the Lorentz transformations, right? So we had gone over this also. So we're reminding ourselves again that one of our invariant quantities is something that looked like this. So we needed to combine a left chiral conjugated spinor with a right chiral spinor. And conversely, we can combine a right chiral conjugated spinor with a left chiral spinor. Okay, and these two guys were invariant objects. And another way to write these guys was through the notation we had written above here. Okay, where we have a downstairs and an upstairs guy, and upstairs and a downstairs guy. And again, dotting them both is, again, equivalent to saying this, or not dotting them both is equivalent to saying this. As long as both of them are dotted or not dotted, then those are invariant quantities. Okay? Invariant quantities that they essentially, when I say, again, invariant quantities, these are quantities that remain invariant under these types of transformations. Okay? So we have these guys. We also want to recall that we could construct 4 vectors from spinor-like objects using quaternions, right? And so that was this notation we had developed earlier. All right. And so in a spinor formalism, this is a little bit weird, but in the spinor formalism, we can construct a vector, right? So again, this is a vector. It's weird that we're calling it a vector again because it's AB, right? Usually a vector looks like this, where A runs through from 1 to 0 to 4, say. But we're not doing that in this case, right? In the spinor formalism, we need 2 subscripts or 2 superscripts, which is again weird, but it's a representation of a vector using quaternions, and in sort of the spinor context. And so we can do the same thing, right, for this operator, right? So this operator, usually we think of it as dx, dy, dz as some sort of vector. But again, in the spinor formalism, we use quaternions and we turn it into what looks like a matrix, right? We turn it what looks into a matrix by doing this, okay? All right. And so it's also somewhat conventional to define these 2 guys here, right? So these 2 guys here are Pauli matrix. We have these bars on the Pauli matrices, where the 0th one is just the identity. Anything to the 0th power is identity, and to the I, this bar here is going to be the same thing as the negative of our Pauli matrix, regular Pauli matrices. Okay. All right, let's take a look at what this looks like. This looks random at first, but everything's sort of going to fall into place, okay? So this guy here, we're going to say, okay, it's going to be equal to this, and let's see why it's equal to this, right? So we can actually multiply. So we take this guy here. If we want this guy to be invariant, we can multiply it on both sides by our spinor metric, right? So this D here and this D here match. This C here and this C here match. And so what's left is B in upstairs and A dot upstairs. That's why we can do this. Again, because this is the spinor metric. We've talked about it before. Here's B upstairs and A dot upstairs. So B upstairs, A dot upstairs. And I'll write, those are the green guys. Okay. Okay, so now, well, our spinor metrics are these 2 guys here. Okay. When we dot, the dotting, again, refers to transposing. And we have now, okay, so we transpose that. This guy stays the same, this guy stays the same. So what does this all show us? This shows us that this guy here, well, when you do all of this, that's just going to be the negative of our spinor metric. Okay? Well, if that's the negative of our spinor metric, that's equal to this. All right, so this guy here is equal to this. This is the important thing we want to show. All right, so this is the important thing we want to show. And all of this was that right there. So the logic again goes, this here is this equals this, and this equaled that, which equals this. Okay, so there's a lot of, it seems a little bit confusing, but this relationship is going to be helpful for us. Okay, really, it's really just a mathematical relationship. It's nothing really physical yet. All right, we can now create 2 invariant objects from all this that we've said. So one invariant object is going to look like this, where we have left conjugated and left conjugated, but one's or left conjugated and left, right? So, and then right conjugated and right. This is weird again because in our other two invariant cases, we had right and left, but in these invariant cases, we have left and left, right and right. So this time we're not mixing the two, but what's going to compensate for this not mixing is this derivative here, the derivative of a Pauli matrix. Okay, so what we can say about this, so we want to recall all this up here. What we can say about this is that, okay, so the derivative of the Pauli matrix, again, here's the Pauli matrix, and this mu refers to which Pauli matrix we're interested in. The A and the B refers to elements of the matrix itself. Okay, and L again is subscripted, R's are superscripted. So we can see, we can match these guys, right? Match these guys here, so that everything sort of turns out to cancel, right? And so A and A dot A and A at the bottom, and we're just left again with these two guys. All right, so let's introduce two matrices. So this matrix here and this matrix here. So this is a gamma matrix. Gamma matrix in the superscript is going to have these two Pauli matrices. Okay, so this is effectively, or essentially, a 4x4 matrix. This guy here, again, is a 4x4 matrix. The only difference between the superscript and the subscript is the negative sign. Again, this is a negative of the Pauli matrix, and this is essentially they're transposes of each other. So when we do this multiplication, we get this right here. Okay, and you can follow this matrix multiplication. It's not too difficult. But essentially what we've done here is we've introduced two new matrices. All right. So what we've done so far is get all the mathematics sort of out of the way. We've developed four invariant objects. Okay. These two guys and these two guys. Two of them again are a mix between L and R, and then the other two are not mixes, but they have L's and L's. Again, they're just not mixed, right? So two invariant quantities are not mixed between left and right chiral spinors, and two invariants are. Okay, second page here. I promise this is only 2 pages. We see that we can construct the invariants now using these gamma matrices. So let's see how we can do this. Consider this guy right here. So this guy here is going to look like this, right? So again, these are our Dirac spinors. Dirac spinors are combinations of Weyl spinors. The Weyl spinors again are left chiral or right chiral. So dagger, these two guys are dagger, and it's this sort of vector right here, and then not with the dagger, again regular vector. That's not in this form, right? Because when it's in this form, that's what this dagger implies. Okay, so we're essentially conjugating this guy right here. So the conjugate of this guy is this guy right here. That's what this is showing. And then we have our gamma matrix. Okay, well, when we do this multiplication, we get this, which is super interesting, right? Because here's a mix between our L and our R, mix between our R and our L. Again, this guy refers to the conjugation. And so this is really just our I1 and I2, right? Because if we're doing 0, we said here, right? We said way down here, 0 refers to just the identity. Okay? 0 refers to identity, so that means we're just looking at these two guys for our invariant objects. So we've packaged our two first invariant objects into this guy right here. Okay? We're going to package the other two invariant objects into something that looks like this. Okay? So that's what this all looks like. Okay? Right, because the derivative, right, so this guy here is our Pauli matrices again, and the derivative is just showing up also in this matrix, in the non-zero entries of the matrix. When we do all of this multiplication out, we get something that looks like this. And lo and behold, what would we see here? We see that we have a combination of L and L, and we have a combination of R and R. All right? And we have also shown that combination of these two guys, the derivative with the Pauli matrix, that is just that's what we've shown for I4 and I3 and I4, right? So we have some derivative and we have some Pauli matrix also, and we can actually move the Pauli matrix around here because there's no space-time dependence on the Pauli matrices, and so so that's what we have here, right? So we have those are those two middle terms right here. So to make this a little bit clearer, this is I3, and this is I4. All right. So we've packaged, essentially what we've done is we've packaged I1 and I2 into this term, and we packaged I3 and I4 into this term. So what does that mean? That means that this is an invariant object, and this is an invariant object under this representation. Okay. Again, this representation referring to the transformation that maintains the Minkowski metric. It's just a different representation. It's the transformation that maintains the Minkowski metric, but in spinor formalism. Okay. So all the invariant objects under these Lorentz transformations in this representation are these objects right here, and they got packaged into this guy and this guy. This is useful, right? I really like summarizing stuff like this because it kind of just helps, I think, in consolidating all of this information into one place that you can go back to later. All right, so we are now on the downswing, and we're going to derive the Dirac equation, or the Dirac Lagrangian. We use these two guys because, again, they contain all of these guys. So our Lagrangian is going to be a weighted sum of both of them. And right off the bat, this is our equation. This is our Dirac Lagrangian. We just need to pick constants for A and B, right? So we're going to just say that A is M and B is I. Super simple. And actually, there needs to be a dagger on that guy, right? Let me just double check. Oh, yes, right. So actually, this guy here is the dagger. That's where that's coming from. And also this guy here. Right, we want to remember that when we combine the zero, this zero right here, with the Dirac spinor, we get the bar on the Dirac spinor. It's just a short way of condensing, or it's a way of condensing the notation, essentially. Okay. So now, so we got the constants, and this is our Dirac Lagrangian, right? So our Lagrangian in the 1/2 0, 0 1/2 representation. And lo and behold, we have recovered the Dirac Lagrangian. So using the Euler-Lagrange equation, we can now we can get this equation, right? So this isn't too difficult. We really just plug this into our Euler-Lagrange equation, and when we take it with respect to the non-conjugated, these combinations, and actually, I think here what we need to do. Let's see. I think that actually works, right? Because so we get this guy here, and then similarly we also get this guy here, right? So we're just taking with respect to different fields, right? So one is a conjugate field, and the other one is not, right? And there might be some missing. Let's see if so. With respect to phi, I want to make sure this is okay. So with respect to phi, this is going to be m on this one. Yes, that's okay. And then with respect to phi bar, that's all going to be a constant, that's all the constant in front of phi bar, right? So this should work. So this looks good. And this is our Dirac equation. Okay. Now, one thing I want to mention, again, these two guys down here, you can actually go, the reason we have with respect to phi and phi bar, and phi bar and phi bar, I want to make sure this is actually correct. So the phi bar, let's see, so the kinetic term, actually, I think it has to be like this, right? I'm catching myself right now. Because when we do that, then the other term has to be the bar term. Yes, okay. And that's in front of this, okay. So that's where the mess up was, right? So these two guys are, this guy here is not bar, this guy here is also not bar. These two, this is bar, right? And when we take respect with the bar, we get the Dirac equation, okay? And then this is also a conjugate to the Dirac equation. But this is what we call the Dirac equation, just notationally. Anyways, this was a long video, but what we did is we established the invariant quantities. Again, these are the invariant quantities under transformations, spinor transformations, right? Spinor transformations are Lorentz transformations. They're just Lorentz transformations in the world of spinors, right? So the world of spinors is this sort of, it's not a copy-paste world of vectors, but again, it's a different representation of the 4-vector world, right? In the 4-vector world, we're preserving the Minkowski metric. In the spinor world, we're preserving the spinor metric, but the representations are one and the same thing, right? The whole idea of representation theory is that these two things are essentially one and the same thing, okay? And so we have invariance in our 4-vector world, we have invariance in our spinor world, and we have invariance in our scalar world, right? So I actually didn't talk about the 4-vector world. Yeah, that's going to be in the next video. That's on the Proca Lagrangian. What we've done so far, again, is looking at invariance in the spinor world, right? And we also, that was this video. And we also looked at invariance in the scalar world. So we're now done with scalars and spinors. We're now going to move on to 4 vectors. And again, 4 vectors being part of special relativity. And those guys are going to be, those invariants are going to be very, very important in how we go forward in talking about interaction theory. With all that being said, this was a long video, but it was well worth it. I hope you guys really, really like this content. Again, if you want it early, you can go onto my Patreon page, or you can just wait for all of it to come out eventually. And again, please hit that like and subscribe button. This channel is doing great. I love the progress of this channel. I am very close to finishing some stuff on the personal front. And after that, I'm going to really be accelerating more and more content out there. I'm going to be making more exclusive content. And I'm going to be really diving into I really want to make this channel something special for all of you guys who are interested in physics, all of you guys who are interested in other areas of science, medical, physiology, neuroscience. All of this stuff is super, super interesting to me. I've been reading and studying a lot of this for a long time. So yeah, with that being said, please make sure to hit that like and subscribe button. Go onto my Patreon page. Also, I'm starting a Twitter account for those of you who want to follow me on Twitter. Anyways, I will see you guys in the next one.